Hello, I'm Matti Koivusto from DTU. In this video, I will be presenting wind power modeling in the PECD version 4.2. We will be looking at how to translate wind speed into power generation. We will look at local scaling of the wind speed data. Please note that there's a separate video about the climate and weather data and the general bias adjustment procedure. But here we will look at the specifics on what do we do with the wind speed data to scale it locally for even higher accuracy. We will also look at an overview of the simulated wind generation cases in PECD 4.2. When going from wind speed to power generation, first we need to interpolate or extrapolate the wind speed to the proper hub height. So we use a unique hub height for every wind power plant. We also need a power curve for every wind power plant. And here we can note that when modeling the existing onshore wind installations in Europe, we have more than 10,000 wind power plants. So we also estimate more than 10,000 power curves. These are generic power curves based on generic technical parameters. We do not use specific manufacturer power curves. Considering a turbine power curve, so power curve for a singular turbine, we use specific power, turbulence intensity, and rotor diameter. So we need to have these inputs for every wind power plant we want to model. And on the right-hand side, you can see an overview of the impact, how these parameters impact the power curve. When going to plant level, so plant has multitude of wind turbines. There are also wake losses which decrease the power generation compared to the turbine power curve. We thus need some additional parameters to estimate the power curve. We need the number of turbines for the plant and also the installation density. These inputs we have either known or estimated for every wind power plant we simulate. Based on that, we can get a plant power curve for every wind power plant. In addition to the part of the power curve up to something like 25 meters per second, we also model the storm shutdown action. We can model different types of storm shutdowns. In addition to the shutdown, we also model the restart operation that happens when the wind speed gets a bit lower, something like 20 meters per second. In addition to the power curves, we need detailed information of wind speeds. We already have the weather and the climate data available, bias adjusted, but it's on the ERA5 grid resolution, so the top figure on the right. We want to use even higher resolution wind speed because we do know we have more information about the locations of the power plants. So the bottom figure shows the global wind atlas resolution, so we use that to estimate the wind speeds at every wind power plant. That is what we call the local scaling of the wind speed data. Here is an overview of the different type of runs we do in PECD 4.2 for wind power. We have a validation run, which is used to validate the methodology against measured data. In this run, importantly, we adjust the wind power plant locations and technology data for every different year. So if there are higher hub heights installed, different type of turbines, it's going to be included in the run. In the existing run, we use the 2020 wind power plant locations and technology and keep it fixed. But we run that over the 40 plus historical weather years and all the climate projections. For future technologies, we also run it over the past weather and the future climate projections, but we run it with several different types of technologies with different hub heights, different specific powers. And that is to model the new installations expected to happen in the system towards 2050. Here is an example of how we use the validation run to validate the methodology. On the left-hand side, there are some validation figures for France, on the right-hand side for Sweden, and also comparison to PECD 4.1. We are happy to say that the PECD 4.2 validates significantly better than PECD 4.1. For example, for France, you can see that the generation histogram shape is closer to the measurements. We also get a correlation that's close to 0.99. On the right-hand side, for Sweden, we also get a correlation significantly higher compared to PECD 4.1, and both the capacity factor and the generation histogram are much closer to the measurements. For the existing run, on the left-hand side, we can see the different wind power plants across Europe that we simulate, and as mentioned, we do simulate every one of those individual wind power plants with the unique hub height, unique power curve. On the right-hand side, you can see an overview of the hub heights of those power curves in the different PECD regions, and that is just to highlight that it's important to have that knowledge of the different hub heights, different specific powers across Europe to model that significant differences. For example, in Finland, Southern Germany, very high hub heights compared to most other regions having significantly below 100-meter hub heights. Those, of course, all impact the simulated capacity factors. Then we have the future technology runs, where we simulate 9 different onshore wind technologies with varying hub heights, different specific powers, and 2 offshore wind technologies. And these are to model the potential new wind installations going forward. The hub height, of course, impacts the effective wind speeds of the plant. On the right-hand side, you can see a visualization of how the specific power impacts the power curve and thus increases, so a lower specific power produces more at a given wind speed. Thank you very much. That was an overview of the PECD 4.2 wind modeling and the different wind runs. Thank you.